Thank you for attending. I would be presenting our paper, Visual Tactile 6D pose estimation of an in-hand object using vision and tactile data. When we estimate the 6D pose of an object grasped by a robotic gripper using vision data alone, only the front half of the object can be captured, even in case of minimal occlusion. Addition of tactile data helps alleviate this problem by providing information of the back of the object and of areas occluded by the finger, thus leading to a better pose estimate. The inputs to our model are color and depth images from a camera which are semantically segmented to obtain cropped RGB and depth images of the object of interest, and tactile sensor information in the form of an object surface point cloud. Our network consists of a visual channel that includes RGB and depth embeddings fused at a pixel level, and tactile channel consisting of depth and tactile embeddings which undergo a pointwise fusion. These features, along with the global feature, are fed to the pose estimator to estimate the 6D pose of an object. We collect a large synthetic domain randomized dataset for 11 objects using the Unreal Engine and NVIDIA's Deep Learning Dataset Synthesizer plugin. We deployed our network on two different setups with different grippers and tactile sensors. The first setup consists of Vice gripper with two gel-side tactile sensors. The second setup consists of a multi-finger robot hand with pressure-based tactile sensors. The baseline is a modified version of our network in which the tactile channel has been removed. It is trained on the same dataset as our network, but with vision data alone. The white point cloud represents the ground truth, the green point cloud represents our network, and the blue point cloud represents the baseline. The plot to the bottom right corner displays the live angular and position error with respect to the ground truth pose obtained using a motion capture system. Since these are error plots, the lower the value, the better the performance. We notice the baseline estimate is unstable while our network maintains a good pose estimate. These are examples of when the network is tested on different objects. This is our second setup. The right image is from the main camera looking at the robot, and the left image is the depth point cloud from the main camera. Here, we vary tactile input to the network by changing the robot fingers in contact with the object. Here we see that as we gradually increase the occlusion level, our network maintains its pose estimate while the baseline becomes unstable. In this paper, we presented a novel approach to estimate the 6D pose of an in-hand object using vision and tactile data. We proposed a tactile sensor agnostic representation. We introduced a visual tactile network architecture in which data from vision and tactile sensors are fused in a meaningful way. We presented experiments in which we showed that networks trained with vision and tactile data outperforms one trained with vision data alone. We demonstrated that a network trained in synthetic data can be successfully transferred to a physical robot.